In this video SOP, we'll take a look at the Alfa Laval M20 cross-flow filtration system and learn how to set up and operate the equipment for use in processing material generated from microbial fermentations. The M20 consists of two functional units: a plate and frame style press that can be used to evaluate various flat sheet membranes simultaneously, and a pair of larger cylindrical housings that are used to evaluate spiral wound membranes at a considerably higher throughput. This SOP will focus on utilizing the M20 with the larger filter housing to process large volumes of material in microfiltration or ultrafiltration applications. A high-pressure diaphragm pump supplies feed material and can be routed to either the flat membrane housing or the cylindrical housings. Optionally, the feed material can be routed through a heat exchanger to provide cooling to sensitive materials before entering the membrane housings. Considerable heat is generated over time as the feed material is pumped through narrow channels at high flow rates. The cylindrical membrane housing may be configured to run with a single membrane or two membranes in series. Safety. There are a number of important hazards to be aware of while operating the M20 filtration system. The M20 requires a high voltage electrical power source in order to drive the pump. In the unlikely event of a malfunction, shock or arc flash from a 480 volt source can cause serious injury or death. Therefore, it is critical that researchers have completed the requisite electrical switching training and wear appropriate PPE while powering the equipment. The process floor may be crowded with various containers and hoses, and the floor may be wet at certain times. Therefore, it is advisable to wear slip-resistant safety shoes and to be mindful of the appropriate paths around the equipment to avoid tripping hazards. Hazardous material handling, including biological material and caustic cleaning solutions. Heavy equipment, including the M20 skid, holding tanks, drums, buckets, and scales. Equipment setup. A hose is connected to the digital flow meter attached to the feed inlet port below the small feed tank via a sanitary tri-clamp connection. Then the three-way valve is switched to allow flow from the feed hose. Connect a pressure gauge to the inlet manifold to allow the inlet pressure to be monitored. At the outlet end of the filter housing, a retentate manifold is connected to the outlet on the outside of the filter housing. The manifold includes a back pressure valve, a pressure gauge, and a hose to route the retentate flow to an external vessel. Likewise, the permeate manifold is connected to the outlet port in the center of the end cap, which includes a pressure gauge, hand valve, and a hose to external vessel. Lastly, make the hose connections to provide chilled water to the heat exchanger, where the supply line is connected to the bottom side port, and the return line is connected to the top side port. The unit is now fully assembled. Membrane installation. First, remove the end cap on the outlet side of the filter housing. This is done by unscrewing the two bolts that clamp the cap to the housing. A wrench may be necessary if these are tight. Then, the two sides of the clamp are removed and the end cap is separated from the housing. The M20 is compatible with membranes with a 2.5-inch outer diameter and a length of 38 inches, often referred to as a 25-38 membrane. The ATD or anti-telescoping devices are installed on the membrane. The ATD with a blank is inserted on one side of the membrane. Then, the ATD with a connection is inserted into the other end. The membrane is then inserted into the housing with the blank ATD towards the inlet side and the connecting ATD towards the outlet side close to the technician, as seen here. Before fully inserting, the ATD is first connected to the end cap, facilitating the connection to the permeate outlet line. Now the membrane is fully inserted into the housing and the end cap is reinstalled. The end cap clamp is secured with fastening hardware and then tightened with a wrench until the clamp is secure. Utilities. After donning leather gloves, the electrical cord may be connected to a 480-volt power source. The technician then steps to the side of the breaker box, looks away, and switches the breaker to the on position. Both valves for the chilled water supply and return are open to allow recirculation to the house system. Next, the supply valve for the ROD water is opened. A ROD water hose is used to supply water for priming and cleaning tasks throughout the operation. Here, a bucket is filled with water that will be used in subsequent steps. Startup. The operation begins with all the inlet and outlet hoses placed in the water bucket to recirculate while the system primes. Ensure all valves are open, clamps are secure, and there is no back pressure applied on the retentate outlet manifold. The pump is then switched to the on position, and water will begin circulating and priming the membrane. A knob may be used to increase or decrease the pump speed, corresponding to the feed flow rate and inlet pressure. The flow rate can be monitored via the digital flow meter near the feed inlet port. Take care to monitor the inlet pressure while adjusting the flow rate to not exceed manufacturer specifications, which may damage the membrane. Continue to monitor the streams as the system runs in full recirculation mode for at least 10 minutes to ensure that there are no leaks and that the system is fully primed with liquid. Process parameters. Here we will give an overview of the key process parameters and controls involved with running the M20 system. The three key parameters are the feed crossflow rate, the transmembrane pressure or TMP, and the pressure drop or DP. It is critical that each parameter is operated within the range as specified in the membrane product documentation to ensure optimal process performance and to avoid process failure or damaging the membrane. The feed crossflow rate is mainly a function of the feed pump speed, which can be adjusted to increase or decrease the crossflow rate. Providing a higher crossflow rate will assist in displacing particulates before they can settle and foul the membrane pores. Increasing the crossflow rate will also increase the inlet pressure on the feed. In this example, the inlet pressure is read at 31 psi gauge and the retentate outlet pressure is read at 22 psi gauge for a total pressure drop of 9 psi. The transmembrane pressure, or TMP, is the measured difference between the permeate stream and the crossflow stream pressures, the latter of which is calculated using the average of the feed inlet and retentate outlet pressures. This yields an effective measure of the driving force between the two sides of the membrane. Permeate flux will generally increase as the TMP is increased, at the expense of increased accumulation of material that may ultimately lead to membrane fouling. The TMP can be manipulated in a couple of ways. 1. Adjusting the pump speed and associated feed pressure, or 2. Adjusting the retentate back pressure valve to restrict retentate flow but maintain higher pressures on the feed side of the membrane. When using spiral wound membranes, no back pressure should be applied to the permeate line, and this should remain at atmospheric pressure. In this example, the permeate outlet is measured at 0 psi gauge, which along with the other pressure readings results in a transmembrane pressure of 26.5 psi gauge. Lastly, the crossflow is about 20 liters per minute. In general, the goal is to maximize the TMP with a sufficient crossflow rate to prevent premature fouling of the membrane. For instance, running the system with a very high TMP but relatively low crossflow will result in initially high flux that quickly degrades as the membrane pores are overwhelmed with accumulated particulates. A more conservative approach is to start with a high crossflow rate and a low TMP. As the process is monitored, the TMP can be gradually increased. Membrane cleaning. Membranes may be coated with a layer of glycerin or other storage solution and must be thoroughly cleaned before introducing process material. First, a high pH cleaning solution is made up by adding a small amount of CIP 100 to the water. Be mindful of the hazards of working with caustic solutions. A pH test strip can be used to verify that the pH is around 11. Now, the solution can be recirculated for 30 minutes. The caustic solution will be gradually flushed out until a neutral pH is reached on the permeate outlet stream, as measured with a pH test strip or pH meter. Clean water flux. Now that the membrane is cleaned, a test is conducted to verify the clean water flux is within the manufacturer's specifications and that the membrane is behaving as expected. It is also useful to record this value over subsequent processing runs to monitor degradation of the membrane over time, after which it must be replaced. The clean water flux is measured by collecting the permeate stream for a given time period, such as 1 minute. Then, the mass of water is used to calculate a flow rate and flux value using the membrane surface area. In this example, the clean water flux is 167 liters per square meter hour. Material processing. Now that the membrane performance has been validated, the filtration of the processed material may begin. The feed hose is placed in the holding vessel containing the input material, drawing material into the pump. The permeate hose is fed to a different collection vessel. The retentate hose is also placed in the vessel of input material, allowing the recirculation of unfiltered crossflow. The primary process parameter is the flux of permeate across the membrane, which is a function of multiple related factors, including the crossflow rate, the TMP, and the properties of the feed material. As discussed, the crossflow rate must be sufficiently high to maintain flux levels over the course of the filtration process by preventing membrane fouling. The permeate flux is measured throughout the processing to monitor potential fouling of the membrane. As before, the permeate stream is collected over a given time interval and converted to a flux value using the membrane filter area. Here, the permeate flux is measured at 12 liters per square meter hour. Post-experiment cleaning. After the material has been fully processed to desired specifications, the system will need a thorough cleaning, beginning with a water flush. Fresh water is supplied to a bucket where the feed, retentate, and permeate hoses are placed. Then the pump is started so the water is allowed to recirculate with periodic flushes to the drain while replacing with fresh water. Next, CIP100 is introduced to create a caustic cleaning solution that will better clear material from membrane pores and surfaces. Again, all hoses are placed in the CIP solution bucket and the solution is recirculated for 30 minutes. Now the permeate and retentate lines are routed to the floor drain manifold and fresh water is introduced to the feed bucket. The system will continue flushing with fresh water until a neutral pH is reached on the permeate outlet stream. Lastly, the clean water flux is measured in the same manner as before the processing. The end value should be similar to the original value, thereby validating that the membrane has been thoroughly cleaned and may be reused in future applications. The membrane is typically stored in a pH 9 solution that can be made using CIP100.